Dear students, welcome. Today we shall start a new chapter which is called the moment and parallel force. Moment and parallel force. Parallel forces. First, let me define the moment of a force. Moment of a force. Moment of a force. It is about a point. Moment of a force about a point. Suppose F factor is a force. We have to find the moment of the force about a point O. About a point O. Suppose A is any point in the line of action of the force A, F. Suppose OA vector is R vector. Then R vector cross F vector is called the moment of the force F about the point O. Let A be any point in the line of action of the force F. In the line of action of the force F. Any point of the line of action of the force F. We have to find the moment of a force about the point O. The moment of the force F about the point O. Point O is defined as R vector cross F vector, where R vector is the position vector of A, where R vector is the position vector of A. R vector is the position vector of A with respect to O. R vector cross A vector. Thus, if M is it will be a vector quantity. It is a cross product of two vectors. It will be a vector quantity. If M is the moment, then M vector equal to R cross F vector. R cross F vector. Just find the magnitude of the moment. M vector, this equal to the magnitude of the moment. The magnitude of the moment M. Then M vector, this magnitude should be equal to R cross F vector. R cross F, the magnitude of this. Suppose the angle between R and F is equal to theta. This is equal to theta, which is equal to R OA F into sine of the angle between these two vectors, sine theta. F sine theta. This can be written as F OA sine theta. Suppose ON is perpendicular on the line of action of the force. ON is perpendicular on the line. Then ON by OA will be equal to sine theta. ON equal to OA sine theta. This is equal to F into ON. Suppose the distance is P. This is equal to Fp. Thus the magnitude of a force about a point is the product of the magnitude of the force and the perpendicular distance from the point to the line of action of the force. You may write like this. Thus, the magnitude of the moment of a force, thus the magnitude of the moment of a force about a point O is the product of the magnitude of the force and the perpendicular distance from the point O on the line of action of the force. The magnitude is what is the magnitude of the moment of the force F about the point O will be equal to F into this distance from the point O. Take the perpendicular distance from the point O and the perpendicular distance from the point O to the line of action of the force. Line of action of the force. To the line of action of the force. Now, suppose B is another point. Next, suppose B is another point. Suppose B is another point. And another point on the line of action of the force. On the line of action of the force F. On the line of action of the force F. Then OB vector cross F vector will be equal to, what is OB? Will be equal to OA plus AB. AB cross F vector. This is equal to OA vector cross F vector plus AB cross F vector. AB cross F vector will be equal to 0 because angle between them will be equal to 0. OA cross F vector. Since AB cross F will be equal to 0, you should write the vector sign because the product of two vectors is a vector quantity. OA cross F equal to moment of the force. The force F about the point O. About the point O. Moment of the force F about the point O. Therefore, what is the moment of a force about the point O? If you take any point, any other point C on the line of action of the force, then the position vector of that point with respect to the origin O, with respect to the point O, is whatever it may be. Suppose it is R vector, R1 vector, R1 vector cross F vector will be equal to the moment. Therefore, you may it is independent of the point A. Independent of the point A. You may choose any point on the line of action of the force F. This means that OB vector cross F vector is again the moment of the force about the point A. OA vector cross F vector equal to OB vector cross F vector. It is the moment of a force about the point. Now, I am going to give you the statement of an important theorem, which is called the Perignon's theorem on moment. Perignon's theorem on moment. What is the Perignon's theorem on moment? It is true for concurrent forces, or it is true, and it is true for parallel forces. I will discuss the Perignon's theorem for parallel forces later on. What is the Perignon's theorem on moment? The algebraic sum of the moments of two forces acting at a point is equal to the moment of their resultant about the same point. The algebraic sum of the moments of two forces acting at a point about any point in their plan is equal to the moment of their resultant about the same point. What is the statement of this statement? The algebraic sum of the moments of two forces acting at a point. For parallel force also it is true. For parallel force also it is true. I am giving you the definition for the concurrent forces. Therefore, that is why I am writing acting at a point. About a point O in their plan is equal to the moment of their resultant to the moment of their resultant is equal to the moment of their resultant about the same point O. About the same point. Suppose P and Q are two forces. P and Q are two forces acting at a point A. R is the resultant. R is the resultant of P and Q. You have to find the moment of the force about the point. Suppose the forces P and Q are acting at the point A. Acting at the point A. Let R be their resultant. Let R be their resultant. Let R be their resultant. Therefore, R vector will be equal to P plus Q. R vector will be equal to P plus Q. The resultant of P and Q is R. We have to find the moment of the force P about the point O will be equal to OA vector, because A is a point on P. OA vector cross P vector. Therefore, now the algebraic sum of the moments of the forces P and Q about the point O should be equal to OA vector cross P plus, what is the moment of the force Q about the point O? It will be again OA vector cross Q. This is equal to OA cross P plus Q. You may write like that, P plus Q. This is equal to OA cross R vector. This is equal to moment of the resultant R about the point O. This is equal to moment of the resultant. The resultant about the point O. Moment of their resultant about the point O. This is the proof of Perignon's theorem for concurrent forces. If the algebraic sum of the moments of two forces about a point is equal to the moment of their resultant about the same point. About the same point. from this theorem, you may suppose about the point O. The point O is on the line of action of the resultant. Then you see what is the moment of the force about a point equal to product of the force and the perpendicular distance from the point to the line of action of the force. Now, if the point is on the line of action of the force, then the moment will be equal to 0 because the perpendicular distance of the point, perpendicular distance from the point to the line of action of the force is 0. Therefore, the moment will be equal to 0. Now you see the moment of a force about a point. The moment of a force about a point. The moment of a force about a point which is on the line of action of the force. Which is on the line of action of the force is always 0. Moment of a force about a point. The point is on the line of action of the force. It will be 0 because the perpendicular, what is the definition of moment of a force about a point? Is equal to the product of the force and the perpendicular distance from the point to the line of action of the force. From the point to the line of action of the force. Therefore, the perpendicular distance is equal to 0. Therefore, the moment will be obviously equal to 0. Now, here, if from Perignon's theorem, the algebraic sum of the moments of two forces about a point which is on the line of action of their resultant will be definitely 0 because the algebraic sum of the moments of the forces P and Q about a point is equal to the moment of their resultant are about the point, but the point lies on the resultant, line of action of the resultant. This means that the moment of their resultant about that point will be equal to 0 by Perignon's theorem on moments. Therefore, you can conclude that the algebraic sum of the moments of the forces will be also 0. Now, you may write the algebraic sum of the moments of two forces about a point which is on the line of action of their resultant. The algebraic sum of the moments of two forces about a point which is on the line of action of their resultant will be 0. Because the moment of the force about their resultant will is 0, therefore by Perignon's theorem, the algebraic sum of the moments will be also 0. Now, you see, if the forces are in equilibrium means the sum of the forces is equal to 0. Therefore, by Perignon's theorem, you may say that algebraic sum of the moments of a number of forces about any point in their plan will be equal to 0 if the forces are in equilibrium. Because if the forces are in equilibrium means their resultant is 0. The moment of the force which is 0 about any point will be equal to 0. Therefore, the algebraic sum, if the forces are in equilibrium, then the algebraic sum of the moments of the forces about any point will be equal to 0. Also, if the algebraic sum, sum of the moments, of a number of planar forces about any point is equal to 0, then two cases arise. Number one, the forces must be in equilibrium. Number two, the point must pass through the point must lie on the line of action of the resultant, or in other words, the resultant must pass through that point. You see this one. Through that point. Now, first, let me write the generalized theorem on Perignon's theorem. Generalized Perignon's theorem on moment. Generalized Perignon's theorem of moment. If a number of coplanar forces acting on a rigid body, suppose on a body would have a resultant, then the algebraic sum of the moments of their moments about any point, the algebraic sum of their moments about any point is equal to the moment of their resultant. Is equal to the moment of their resultant. Let P1, P2, P3 up to Pn be concurrent forces. And let R be their resultant. Then R vector equal to P1 plus P2 plus P3 plus up to Pn. Suppose P1, P2, P3, suppose Pn, and suppose their resultant is R. Suppose O is any point. Now the algebraic sum of the moments of the forces P1, P2 up to Pn, P3 up to Pn, suppose Pn about the point O point O will be equal to OA. From the diagram you see cross P1 vector plus OA, P2 plus OA, P3 plus plus OA, Pn. The moment of the force, sum of the moment of the forces, P1, P2, P3 about the point O will be equal to this. From this you may write OA cross P1 plus P2 plus P3 plus Pn. This should be equal to OA cross R vector. This is equal to moment of the resultant R about the point O. This is equal to the moment of the resultant R. R about the point O. About the point O. Moment of the resultant R about the point O. Perhaps you have understood the Perignon's theorem on moment. Sum of the moments of the forces about any point equal to the moment of the resultant about the same point. This is the now you may find the conclusion. Number one. If a number of coplanar forces acting on a body, if the number of coplanar forces acting on a body have the resultant are in equilibrium, suppose are in equilibrium, then their moment, sum of their moment should be equal to 0. How? Because the moment of their resultant is 0. Therefore, algebraic sum of their moment should also be equal to 0. If a number of coplanar forces acting on a body be in equilibrium, then their resultant will about any point will be equal to 0. Resultant will be equal to 0. Therefore, then the algebraic sum of their moments about any point in their plan, will be equal to 0. Definitely you will get this one. Apply the Perignon's theorem on moments. Number 2. Equilibrium means this one. If the algebraic sum of the moments of a number of coplanar forces acting at the body, acting on a body, algebraic sum B0 be equal to 0, then either they are in equilibrium, either the forces are in equilibrium, or then either the forces are in equilibrium. Either the forces are in equilibrium, then either the forces are in equilibrium, or the line of action, forces acting on a body about if you say the moment of a force, then you will have to say that about a point or about a line on a body. About a point O, say, about a point O, say, B equal to 0, then either the forces are in equilibrium or the line of action of their resultant passes through that point. The point passes through the point. The algebraic sum of the moments of a number of coplanar forces is equal to 0, given by Perignon's theorem on moments. The moment of their resultant should be also equal to 0. The moment of their resultant is also 0. What is the moment of their resultant? If the moment of their resultant is 0, then the force must be equal to 0. Number 1 case. Case number 2. The point must lie on the line of action of the force of the resultant, so that the perpendicular distance of the point to the line of action of the resultant is equal to 0. Therefore, or the line of action of the resultant passes through the point O. The two cases will arise. Now you have understood this one. Physical significance or some related conceptions will be given later on. Now let me define the parallel forces. Let me define parallel forces. Parallel forces. When two forces never meet at a point, two forces P and Q, their line of actions never meet at a point. They are always parallel. Two forces are said to be parallel forces if their lines of action never meet at a point. Parallel forces if their lines of action do not meet. Lines of action do not meet at a point. Now, like parallel forces, this is a force P, this is a force Q. If the sense of directions are same, the directions are in the same direction. These are two like parallel forces. And unlike parallel forces, they are parallel. If P is acting in this direction, Q will be acting in the opposite direction. These are unlike parallel forces. If P forces this and Q forces this, then they are unlike parallel forces. You are to remember that the two forces are not equal. If they are equal, then P equal to Q. Then the two forces are said to form a couple. It will be a couple. We will discuss about couple later on. It will be a couple. the two forces P and Q for unlike parallel forces. For like parallel forces, this restriction is not applicable, but for unlike parallel forces, the forces should be unequal. If it is equal, then we say that it will constitute a couple. These are unlike parallel forces. Like parallel forces and unlike parallel forces. Now let me tell you the resultant of like parallel forces Suppose P force is acting in this direction at the point A. Q force is acting at the point B. The resultant of two like parallel forces, the resultant of two like parallel forces P and Q is P plus Q, which is again a like parallel forces, which is again a like parallel force, and will be acting two like parallel, the resultant of two like parallel forces, even which is again a like parallel force. Suppose P and Q are acting at A and B respectively. Suppose P and Q are acting at A and B respectively, then their resultant P plus Q will be acting at C. Suppose C, then the resultant will be acting at C such that P into AC equal to Q into BC. You should remember this one. P into AC, so P without the vector sign will give you the magnitude of the force P, and Q without the vector sign will give you the magnitude of the force Q. P into AC equal to Q into BC. From this, it is clear that if P is greater than Q, then C, the line of action C, will be nearer to the force P. And if Q is greater than P, then C will be nearer to B. It is obvious because P into AC equal to Q into BC. The product should be equal to same. This can be established very easy. You can establish it. Let me write. Suppose P force is this, Q force is this. We will introduce another force F and minus F. F at A and minus F at B. The combined effect will be equal to 0. Now the forces P and F acting at A. The resultant will be equal to this. What is the resultant? P plus F. It will be P plus F. And Q and F, the resultant will be equal to Q minus F. Q minus F. It will be Q minus F. Suppose it acts at the point O. In this way, we can show that the resultant will be equal to P plus F and Q plus, by the law of transmissibility of forces, the forces acting at A and acting at B can be shifted to the point O. Now the resultant of Q minus F and P plus F will be equal to P plus Q. It will be parallel to this. In this way, we can find that the resultant of the two like parallel forces P and Q is P plus Q, and the resultant will be acting in the line AB, at the point C in such a way that P into AC equal to Q into BC. Just remember this one. For unlike parallel forces, resultant of two unlike parallel forces, the resultant of two unlike parallel forces P and Q. Suppose the magnitude of P is greater than the magnitude of Q. The resultant of two unlike parallel forces P and Q. P is greater than Q. Suppose P is acting in this at the point A. Q is acting at the point B. Q is acting at the point B. Then the resultant will be acting in a line BA at the point C in the line BA produced, and it will be like to the point to the force P. The resultant will be equal to P minus Q and will be acting at the point C in such a way that P into AC equal to Q into BC. P into AC equal to Q into BC. Suppose Q is greater than P. Q is the magnitude of Q is greater than P. Then suppose this force is P and this force is Q. This is A. Suppose this is B. Then the resultant will be equal to P minus Q or Q minus P. Resultant will be equal to Q minus P, and it will be acting at the point this. Such that Q into BC equal to P into AC. P into AC. For unlike parallel forces, the resultant will be P minus Q, and it will be acting. If P is greater than Q, then P into AC equal to Q into BC. If Q is greater than P, then the resultant will be in this direction. Direction of Q and the resultant Q minus P will be same. And Q into BC will be equal to P into AC. This is the case. And you can prove the Perignon's theorem for parallel force also. Perignon's theorem is valid for parallel force also. If P and Q are parallel forces, their resultant is P plus Q. Then the algebraic sum of the moments of P and Q equal to the moment of their resultant about the same point. The algebraic sum of the moments of P and Q about any point is equal to the moment of their resultant about the same point. The Perignon's theorems can be applied. Now let me solve some problems, simple problems. Let us try to solve these three problems. Now what is this? Question number 1. If the position of the resultant of two like parallel forces P and Q is unaltered when the forces are interchanged in their positions, prove that P equal to Q. Suppose P and Q are acting at the point A and B respectively. A and B respectively. Suppose that the forces, the like parallel forces, P and Q. Suppose that the like parallel forces P and Q are acting at the point A and B respectively. A and B respectively. Acting at the point A and B respectively. Their resultant R equal to P plus Q will be again a like parallel force. Again a like parallel force acting at C P plus Q, acting at C such that P into AC equal to Q into BC. P into AC equal to Q into BC. Suppose this is number 1. This is number 1. Now, let the positions of Q and P and Q are interchanged. Let the positions of P and Q are interchanged. Suppose Q is acting at A and P is acting at B, their resultant will be Q plus P. That is, let P and Q are acting at B and A respectively. In this case, when the positions of P and Q are interchanged, then their resultant will be acting at C. Then also their resultant P plus Q will be acting at C such that in this case Q into AC equal to P into BC. Suppose this is number 2. Now dividing 2 by 1 we get, or 1 by 2, dividing 1 by 2 we get 2 we get. Divide 1 by 2. P into AC by Q into AC. P by Q equal to Q divided by P. AC and BC will be cancelled. This means P square is equal to Q square. This means P equal to Q. This means that P equal to Q proved. P equal to Q proved. Therefore, we have proved number 1. It is very easy. Let me remove number 1. We have proved number 1. Number 2, see the question number 2. What is it? Two like parallel forces P and Q at two given points A and B. At two given points A and B. A and B. P and Q at two given points A and B respectively. If two forces S and minus S are combined with them, secondly, in the second case, S is added to this and S subtracted from Q. Suppose if for the in the first case their resultant is P plus Q, will be acting at C, and in the second case let me write like this, because it is it will be, suppose it is acting at C, because suppose P is greater than Q, then it will be nearer to P. The resultant R equal to P plus Q is this first, for the first case. In the second case, it will be P plus S is greater than Q minus S, definitely, because S is added to P and S is subtracted from Q. Therefore, the resultant will be moving in this direction towards A. Resultant will be moving towards A. Therefore, the new resultant will be acting at the point C, at the point D. Suppose like that. At the point D, we have to find the resultant is displaced through a distance this S into AB divided by P plus Q. Means we have to find the distance between C and D. We have to find the distance CD. Let the forces P and Q are acting at A and B respectively. Let their resultant acts at C such that P into AC equal to Q into BC. Suppose this is number 1. P into AC equal to Q into BC. This is number 1. Now, you see, if S and minus S are combined with them, if S and minus S are combined with P and Q respectively, then the new forces, then the forces will be, P plus S and Q minus S. Forces will be P plus S and Q minus S. Obviously, their resultant will be this plus this equal to P plus Q. Their resultant is P plus Q. The new forces will be immanent and will be acting at A and B respectively. Let the resultant will act at the point D, such that P plus S into AD, this is equal to Q minus S into BD, right? Their resultant will be also P plus Q. Sum of the two like parallel forces will be equal to this plus this. This is equal to P plus Q. Their resultant, the new resultant. Let the resultant, you may write the new resultant. Let the new resultant will act at the point D, such that at the point D, then it is obvious P plus S into AB. We have to find the value of CD. We have to find the value of CD. Now from 2 you will get P plus S into, for AD you may write AC minus CD, Q minus S, BD means you may write BC plus CD. BC plus CD. You may write like this. Now, one, it will be applied, therefore I will not remove this. P into AC, this means P into AC plus S into AC, minus P plus S into CD will be equal to Q into BC minus S into BC plus Q minus S into CD. Q minus S into CD. Now, P into AC, Q into BC, these two terms will be cancelled because P into AC equal to Q into BC. This means that P plus S plus Q minus S into CD. Take this term to right hand side, and then you may write S into AC plus S into BC. S into AC plus S into BC. AC plus BC. AC plus BC or AC plus CB. AC plus BC. What is this? Equal to AB. P plus Q into CD equal to S into AB. Here you may write since P into AC equal to Q into BC. Therefore, these two terms has been cancelled. This means that CD equal to S into AB divided by P plus Q. Therefore, the distance between C and D means the resultant is displaced through a distance. That is the resultant if another force S is applied, S is added to the force P, and S is subtracted from the force Q, then the resultant moves through a distance S into AB divided by P plus Q. Resultant is displaced, that is therefore the resultant is displaced through a distance S into AB divided by P plus Q. Resultant is displaced through a distance S into AB divided by P plus Q. Perhaps you have understood this one. We have done the question number 2 also. Now let us try to solve the question number 3. Let us try to solve the question number 3. Now let me remove this one. Question number 3. What is this? Two like parallel forces P and Q acting on a rigid body at A and B be interchanged in position so that the point of application of the resultant is displaced along AB through a distance. Which one? Suppose the two forces P and Q. The two forces P and Q are acting at the point A and B respectively. P and Q are acting at the point A and B respectively, and suppose P is greater than Q, Therefore, the resultant of P and Q will be this. The resultant is acting at the point C. Now, if the point of application of the resultant is displaced along AB through a distance, when acting on a rigid body at A and B interchanged in positions. If the positions of P and Q are interchanged, then the resultant will be acting at the point D. Suppose the resultant is Q plus P. We are in this case also we have to find the distance. Find the distance CD. Original resultant was acting at the point C, and the new resultant is acting at the point D. The resultant is displaced through a distance CD. The CD distance will be equal to P minus Q divided by P plus Q AB. We have to show that. Let two like parallel forces P and Q. Let two like parallel forces P and Q be acting at the A and B respectively. Let two like parallel forces P and Q be acting at A and B respectively. Let the resultant P plus Q be acting at the point C such that it is very important. P into AC equal to Q into BC. P into AC equal to Q into BC. Suppose this is number 1. PAC equal to Q into BC. This is number 1. This is number 1. Now, let the positions of P and let the positions of P and Q are interchanged, or you can positions of P and Q are interchanged. That is, let P and Q are acting at B and A respectively in this case. Then if P is greater than Q, the resultant will be moving towards P, towards this direction, definitely. Let the resultant of Q and P acting at A and B respectively resultant of Q and P is definitely Q plus P. The resultant of two like parallel forces at B respectively. Let the resultant be acting at D such that Q into AD equal to P into BD. This time Q into AD equal to P into BD. Interchange their positions. Now we have to find the value of CD. Therefore, this means you may write Q into, in this case Q is acting at A, P is acting at B. Q into AD equal to P into BD. AD can be written as AC plus CD. This is equal to P. BD can be written as BC minus CD. Or Q into AC plus Q into AC equal to P into BC, or Q into AC you may write like this, plus P plus Q into CD equal to P into BC. You may write like this. Q into CD minus PCD. Take this minus PCD to the left side. You will get this one. This means P plus Q into CD will be equal to PBC minus Q into AC. You may write like this. This is equal to P into what is BC? AB minus AC. AB minus AC. Minus Q, what is AC? AC can be written as AB minus BC. AB minus BC. This is equal to P minus Q into AB minus PAC plus QBC plus QBC plus QBC. P minus, this means P plus Q into CD. This is equal to P minus Q. I am writing once again here. AB minus P into AC plus Q into BC. Now by one it will be cancelled. P into AC equal to Q into BC by 1. This means P plus Q CD equal to P minus QAB, since PAC equal to QBC by 1 this. Therefore, CD equal to P minus Q divided by P plus Q, P plus Q A. Therefore, the resultant is displaced. Therefore, the application of the resultant is displaced. Application of the resultant is displaced along AB through a distance. It will be moving in this direction along AB through a distance P minus Q divided by P plus Q AB. P minus Q divided by P plus Q AB. Proved. Hence proved. Therefore, we have proved the question number 3 also. Dear students, I want to stop here. Such type of interesting problems will be solved tomorrow also. We shall meet tomorrow again. Thanks for attending the class. Thank you very much.